Day 6 is section 3.4, chapter 3. Been doing all this stuff with extrema, maximums, minimums. We learned a little bit about how to find inflection points in intervals of concavity. Well, now we're going to jump to this thing that we're going to call the second derivative test. And what a lot of people will think is that the second derivative test means that you're doing something with the second derivative. Well, the truth is it's a shortcut for finding relative extrema. And I'll highlight the word shortcut because I know how much we like that. But the key word here, you guys, is we're finding extrema. We're not finding anything about concavity or anything like that. So what happens? First off, C has to be a critical number of f prime of x. Critical number. How do we find critical numbers? Well, let's see. So a critical number of f prime of x, we would set f prime of x equal to 0, or we'd find out where it doesn't exist. Those would be the two things we'd be looking for. So we start off by finding the critical numbers of the first derivative. Once we have those values, then if we find out that the second derivative at that particular value is greater than 0, well, what do we normally know about second derivative? We normally know that we're talking about a function that's concave up. So think about what we just put together. We just put together that we have a critical number and concave up. So at a critical number, that's a potential maximum minimum. Well, if it's concave up around it, well, look what we just found. We just found out that the point C, f of C, is a relative minimum. If we find out that at that critical number that I found, the second derivative is less than 0, then I found out that I'm talking about a function that's concave down. Well, if it's concave down around a potential max or a min, then we just found out that the point C, f of C, is a relative max. Pardon me. And lastly, if we find out that at that particular value my second derivative is equal to 0, well, if my second derivative is equal to 0, or my second derivative is undefined, then basically what happens is my test fails. And then we'll go back and we'll use the first derivative test to find out whatever it is that we're trying to look for. So this is meant to be a shortcut. It's not something that you necessarily need to memorize, but the idea would be if I find a critical number and I know its concavity around that critical number, then what I'm going to be able to know is a quick way to figure out if I have found a max or a min. So, all right, second goal here, sketch the graph of the function using all this crazy stuff. So first off, we'll find some extrema. So extrema, normally we'd go through, we'd come up with our first derivative, we'd find our critical numbers, we'd come up with our intervals, all that kind of fun stuff. Well, let's try doing this with the second derivative test. So if we're going to do the second derivative test, the first thing I've got to have is I've got to have my critical numbers of my first derivative. So let's find f prime of x. So my f prime of x, let's see, derivative of 2 sine x would be 2 cosine x. Derivative of cosine 2x would be opposite of sine of 2x, all multiplied by a 2. So there's my first derivative. Now the tricky thing is going to be, now we got to find these critical numbers. So we're going to have the critical numbers of these values. So we're going to set this derivative equal to 0, 2 cosine x minus 2 sine of 2x. And this, for our trig friends, is probably where we ought to spend a little bit of time so we can remember how to deal with some of this trig stuff. So let's take the sine of 2x and let's replace that with the old double angle identity. Let's replace that with 2 sine of x cosine of x. And we'll put everything else back in the problem. Well, what are those two? We now got two terms. I see a 2 cosine x in both of them, so let's factor that out. 1 minus 2 sine of x. And since these quantities are equal to 0, then we're looking for when 2 cosine x is equal to 0. Cosine x is equal to 0, and we're looking for when 0 is equal to 1 minus 2 sine x. So stripping away everything else, I want to know when the cosine is equal to 0. Well, when will that happen? Well, these x values would be 0 and pi. Sorry, let's get those right. How about if we make it pi over 2 and 3 pi over 2? And I'm also looking for when sine of x is equal to positive 1/2. Well, when will that happen? Quadrant 1, quadrant 2, reference angle would be 30 degrees. Pi over 6, 5 pi over 6. So I have 4 critical numbers. So what we're going to do now is we're going to take each of these critical numbers, and in order to evaluate our second derivative test, we're going to do f double prime of each of these four critical numbers. We're going to check out the concavity at each of these critical numbers, so let's go in order with them. So pi over 6 is the smallest, pi over 2 is next, 5 pi over 6, and 3 pi over 2. And what we're going to do is we're going to take each of these critical numbers, we're going to plug them into the second derivative, which we should probably find. So let's find the second derivative while we're at it. So second derivative, f double prime of x. Let's see, so derivative of 2 cosine x would be the opposite of 2 sine of x. Derivative of 2 sine of 2x, let's see, derivative of sine would be cosine still of 2x. It had a 2 in front of it already that we were subtracting. Now we're going to multiply it by another 2, so this is minus a 4 cosine of 2x. And what we're now going to do is we're going to take each of these values and we're going to plug them into that second derivative. So let's plug them into that second derivative. Well, if I do that, I'm going to save us some time here and give you what some of these values are. If I do f double prime of pi over 6, I am going to get f double prime of pi over 6, I'm going to get negative 3. So what does that mean? At x equals pi over 6, the concavity, well, the second derivative is negative, so the concavity would be down. If the concavity is down, that means that our original function has a relative maximum at x equals pi over 6, and then I'd have to go back to my original function and do f of pi over 6 to find its y-coordinate. Well, instead of us going through that, I'm going to give you what that value is. That y-coordinate is 3/2. And again, remember, I went all the way back to my f of x in order to find what that y-coordinate is. F double prime of pi over 2, if I plug that in, I get the number 2. Well, what does that mean? Let's see. So if the second derivative is positive, my function must be concave upward. What did I just find? I just found a relative minimum at the point pi over 2, and again I'll give you the value, pi over 2, and the y-coordinate is 1. F double prime of 5 pi over 6, if I plug that in my second derivative, I get negative 3. So what did I find? Again, concave down. If it's concave down, I just found another relative max at the point 5 pi over 6, and again I'll give you the y-coordinate, 3/2. And last but not least, f double prime of 3 pi over 2. What did I find? F double prime of 3 pi over 2 comes out to be positive 6. What does that mean? That means I'm looking at concave upward. That means I just found yet another relative minimum. And this one is at 3 pi over 2. And the y-coordinate is negative 3. So this second derivative test is meant to help us figure out these relative extrema. It's a faster way to figure out what those relative extrema are, and they're all totally based on the value of the second derivative at those individual critical numbers of the first derivative. So there's second derivative tests. So let's go and let's take a look at this other problem I have set up. Sketch the graph. 2 sine of x over 2 on the interval 0 to 4 pi. Well, 0 to 4 pi, this is crazy. Probably what a lot of people do is they'll look at it and they'll go, oh, these derivatives are going to be awful. This is not going to be good. So I'm going to reverse field on you a little bit here. A lot of people probably would jump right in, first derivative, second derivative, all that fun stuff, some nasty stuff coming. Well, what if we use what we know about graphing trig functions? Let's think back for a second. If we rewrote this thing as 2 sine of 1/2 x, what could we figure out about the graph? Well, we would know that its amplitude would be 2, which means the wave height would go up to 2 and down as low as negative 2. It wouldn't have a vertical shift or a horizontal shift, and the period of this thing, so there, b is 1/2, so the period would be 2 pi over 1/2 or 4 pi, which coincidentally makes sense because that was the interval we were asked to look on. So let's come down here and let's make this graph. Well, if I go to make this graph, let's see if I can zoom it out one more step. Nope, I can't. So if I go to create this graph, I'm looking at a sine graph, and that sine graph has to have a period of 4 pi. There it is. So 2 pi would be in the middle, pi would be that first mark, and 3 pi would be there. It's got to have an amplitude of 2, which makes sense because that's exactly what we've got for those values. So now what's a sine graph normally look like? Well, a sine graph normally starts here, works its way up, works its way back to 0, works its way down. So my sine graph trusting what I know from my days in pre-calculus or working on pre-calculus, there's my sine graph. Well, I can tell you beyond any shadow of a doubt the stuff about this particular graph. Here's a relative maximum at the point pi 2. Here's a relative minimum at the point 3 pi negative 2. And I'm looking at concavity. It looks like, as far as concavity goes, it looks like this thing is concave down on the interval between 0 to 2 pi. And it looks like it's concave up on the interval between 2 pi and 4 pi. And since it's changing there, it looks like I must have an inflection point at the point 2 pi 0. Is that cheating? Mr. Perkins, what are you doing? You're telling us to do stuff that we're not supposed to do here. It says we're supposed to find all these values. Well, what I'd like to remind you of with a problem like this is we've done all this work on graphing trig functions for a reason. And if we know how to create those graphs, let's use them to our advantage. Here's a case where if you can recall what we know about making a sine graph, it can save you a lot of time and derivatives and headaches and stuff like that. So sketching graphs and using the second derivative test as a shortcut, those are today's goals.